let me show you some sky stuff. You know, what's up in the evening and the morning today, and then I'll show you the an image of some of the stuff we'll see in the summer sky, and then go through a few of the new James Webb images that have been being released by NASA and the European Space Agency. So let's dive into it. So I'll look at the sky tonight. We'll look west and look east. And fortunately, with software, we can get rid of the atmosphere and have a dark sky at sunset. So we'll see what's there. Then I'll show you the night sky at high summer, where the center of the Milky Way is high and bright. We can't see it with our eyes. We can look in its direction, but that's where that black hole that was imaged by the telescope the size of the Earth is located, a mere, 27,000 light years away. And then I'll talk about James Webb images from 2023, galaxy images, but also a new image of Uranus, yeah, I can't remember the other. All right, so let's go on the adventure here. So this is my background. It's actually from one of the James Webb images that I'll show you. So here is sunset tomorrow at 7:33 p.m. I could have done tonight, but you can't run out and look at it, or I would rather you didn't. So this would be tomorrow night. So the sun in this image is just below the horizon. And then you see these bright things that start. This is not completely accurate, but it gives a sense. So what are these bright things that first start emerging right after sunset? And so let's look at the cardinal direction. So there's west, the sun now, of course, we passed the vernal equinox, the spring equinox. So the sun is in the northern sky. So it'll set north of west now until next September, when it'll move to the south of west. So there's that. And then here are the other directions, just to make sure you can you're oriented. Now, this is a wide swath of sky. All right, from south to west is a quarter of the sky. So this is a big chunk of sky that we're looking at. And so keep that in mind when you go out to look for stuff. My students in astronomy often react that when they see the constellations in the sky, it's like, it's so big. So yeah, just little screen does not do it justice. It'd be nicer to be in the planetarium, I think. So there, the brightest thing you'll see is Venus. And so it's rising. It came around the far side of the sun and it's moving upward in our sky. It's going to be there through most of the summer. Just lovely. And then way down by the horizon is Jupiter, who's been with us for a long time. All through the winter and spring, we've had Jupiter up there, and we had Saturn. We've lost Saturn. It's on the other side of the sun. So that's where Jupiter is lurking. So it's pretty much lost in the glare. If you're like have a lake that your western horizon is a lake, like Lake Michigan, then you can probably see Jupiter, but it's hard to spot. And then between Venus and Jupiter is Mercury. It's popped up into the evening sky. Mercury's year is about 3 months. So it has 4 years per Earth year. So it pops in the morning sky, pops in the evening sky, pops in the morning sky, pops in the evening sky, every year, every Earth year. So it's very elusive. You got to take the chance to spot it when you can. And then Mars is up here, very faint little thing there. And Mars too has been in our sky a long time. We're leaving it, Earth is leaving it in the dust, so it's getting farther and farther away, and so it's getting fainter and fainter. So let me talk about these planets a bit. Oh, that's right, and Uranus is up there. Now, of course, you can see Uranus without a telescope or binoculars. I have done it, but I had to find it with binoculars first and then hunt for it. So it's best to look for when it's near a bright star. And right now, it's actually pretty much on the other side of the solar system. So it's very, very faint. We want to look at it when we're on the same side of the solar system as Uranus is. And so see that the planets are kind of in a line there. They don't appear just anywhere. They're on a line. And by the way, planet, the root of that word is a bright sky, a bright object in the night sky that moves different from the stars. It's a wanderer. So the Greek root is the word for wanderer. That's where we get planets. And so they're aligned on a thing called the ecliptic. The ecliptic is actually the plane of Earth's orbit. Notice they're not exactly on the ecliptic. They're close. And so the ecliptic is the plane of Earth's orbit because that's what's most important to us. The sun, because we're going around the sun 360 degrees and 365 days, we don't see ourselves moving, right? It took millennia for human beings to figure out, yeah, we're moving. So we move about a degree per day, 360 divided by 365. And so we see the sun moving instead of seeing ourselves moving. And so the sun seems to creep along this line to the east, which is left. Remember, when you look down at a map, east is to your right. When you turn around and look up at the sky, east is to your left. So it's moving to the left along this line about a degree per day. And that's about how far it'll move in April. All right. So you're thinking, well, it's going to catch up with Venus. No, because Venus is moving too. Everything is moving. All right. We're mapping Disneyland from the tilted teacup ride here. And so everything is zipping right along. So the orbits of all the planets are pretty near the ecliptic plane. They don't vary very much. So the planets are always found somewhere along the ecliptic. And they generally move eastward along the ecliptic as we're all going around the racetrack of the solar system in the same direction. Now and then when we pass one of them, they go backwards and in retrograde motion. And this bugged the ancients. It drove them nuts that the planets would suddenly stop and go the other way. That's why they're wanderers. And that's what drove them. Ptolemy made up his complicated patterns with the wheels on wheels. And then Copernicus said, oh, that's ugly. And he came up with the heliocentric model. And then, of course, Kepler came in and really nailed it down and figured out that the planets weren't moving in circles. They're moving in ellipses. And so he came up with the laws of planetary motion and helped us understand the planets. So let's look at that. So this is the solar system orrery. This is from inthesky.org. And orrery is a model of the solar system. Why is it called an orrery? Because the Lord of Orrery, the Earl of Orrery, was the first one to commission one to be built using gears, gear ratios. If any of you were near Union College, they have a lovely mechanical orrery in the Knott Hall, Knott. So this is how the configuration of the solar system tomorrow. So I've got the outer planets have labels, but here is Earth. We're in the third orbit out. There's Mars, Venus, and Mercury. So we're in the inner part, and then the other planets are distributed outward. And so now let's turn this edge on. So here it is more edge on. The blue line represents the ecliptic Earth's orbit. And you can see that the planets, they're all pretty much in the same plane. Here are how much their orbit is tilted from the ecliptic plane. And the maximum is 7 degrees for Mercury, and a little zippy Mercury, and Uranus is less than a degree, about 3/4 of a degree. And so they're all within 7 degrees with Mercury, but leaving Mercury out, the others are all within about 3.5 to 4 degrees. And this is how small that angle is. So that's how much they vary from the ecliptic. So that tells you where you can find the planets. And if you're wondering about Pluto, who is a dwarf planet now, Pluto is tilted at 17 degrees. And Pluto also goes closer to the sun than Neptune periodically. And there's all kinds of other stuff along its orbit. So that's why it's a different class of object. It's a dwarf planet, and they have very different characteristics than the planets. But people are very fond of Pluto. I recognize that. You can get a huggable Pluto, and so I just thought I'd include that for grins. So let's go back to this. And what are these planets doing? Well, Earth passed Jupiter. Remember, we're on the great solar system, the great racetrack of the solar system, and Earth is on an orbit that's faster than Jupiter. So we passed Jupiter every year, every time we go around the sun. We passed it back in September. And that's when it was on that day, it rose when the sun set, and we could see it all night long. And ever since then, we've been leaving it behind, and we're going to leave it behind the sun on April 11th. And so that's coming right up, and then it'll show up in the morning sky, and then Earth will start catching up to it again, and we'll pass it again next year. And then Mercury, remember, Mercury is just zipping around the sun multiple times. It passed behind the sun on the far side of the sun on St. Paddy's Day. It'll be highest in the sky on April 11th, big day, April 11th. And so that'll be a good chance to get out and look at it, though I don't know what the phase of the moon is on the 11th. I have to look that up. If it's I don't know. But so you can go out and check it if the moon isn't horrible for it. And it'll pass Earth, so it'll be between Earth and the sun on May Day, on May 1st. So, like I said, these things are all moving all the time. Venus was on the far side of the sun back in October of 2022. It'll be highest in the sky on May 8th. So it's just rising above the horizon. It's this gleaming white. It is so pretty to look at. It's just dazzling. And the reason it's dazzling is because it's entirely covered with clouds. And those clouds, of course, they brightly reflect the sunlight. They're pretty noxious, though. The clouds are mostly sulfuric acid. It wouldn't be very pleasant to be there. And also, if you're on the surface of Venus, it's about 900 degrees Fahrenheit. Ooh. And the pressure is about 90 times the pressure of Earth's atmosphere. So, yeah, it's some number of Lake Ontario's, the weight of a number of Lake Ontario's. I figured it out for astronomy. I can't remember the number, but it's a very unpleasant place, but it's pretty in our sky. And then Mars, well, Earth passed up Mars on December 8th. That's when it was at opposition, opposite the sun in the sky. And we've been leaving it behind, and we'll leave it behind the sun on November 18th, 2023. So it's going to take Mars, the sun is just below the horizon. So for the sun to catch up to Mars is going to take until November. So then we'll lose it, and it'll pop up in the morning sky again. All right. So let's look again at the orrery. And so here's the outer solar system. And so this is Mars, Earth, Venus, and Mercury in order here, and then the others have labels. So this is April 7th. So let me step this along, and let's look at how the planets move. And so I'll mark these positions later. And so watch little Mercury and Venus. They just zip around in the middle here. And so you can see just those. Here's Mercury over on the left-hand side of the sun. Zing, it's all the way around to the right. I mean, it just zips. So this is, oops, sorry, I've got my numbers disagreeing between the top and the bottom. This is for, this should be 5. Sorry, oh, this label doesn't agree. Okay, so here's May, and now I'll go to June. So here's June. Mercury is going around the far side of the sun again, and these guys have barely moved. All right, Earth now has moved quite a ways. All right, so we've gone through 2 months now. And so, you know, that's a sixth of our orbit. So that's what we've moved. Mars isn't moving very fast. All right. It's moving faster than these guys, but here we all are in July. And then here we are in August. And so here are the planetary positions as they were on April 7th. So you can see how they've moved. So these guys, Neptune, Uranus, Saturn, they barely move in that time. But here's Earth's motion. Jupiter moved a bit, Saturn moved a bit, Mars moved a bit, and Earth went, you know, a good way around our orbit. And so that's how all these planets are moving. And to go from this to what we see in the sky is complicated, so I won't do it. Let's see. So I can't remember the magic. So let me actually get out of that and go to here and show you where I get those orrery pictures. So this is inthesky.org. Yes, in-the-sky.org. And you can go here to the orrery. And of course, you got to get through the ad. Now, the thing that annoys me is they always have it moving. And so the first thing I do is stop the motion. Stop. And then I usually get rid of the projection lines that show you whether the planet is above or below the ecliptic. I just turn them off. And the other thing I get, this is half an astronomical unit. An astronomical unit is the distance from Earth to the sun. And so I usually get rid of that. And here we can zoom in on Mars. And if I can get back up here, the hard part is we're going to see if I can make it just a little bigger. And so that, well, we're going to move the bottom of Mars. And I just wanted to show you, so if we make it the 7th, what I did before, I showed the outer planets. And so here we are on the 7th of April, and then I can go to May. Zing! Did you see Mercury? Whoosh! You know, I mean, it's a third of the way around its orbit, right? It's, you know, its year is 3 months long. And so there's May. Even, let me go back so you can see that motion again. I mean, these inner planets just rip. And then if we go to June, zing, Mercury's all the way around the other side. Here's Earth. You can see the months marked off on this. And then on to July, and Mercury's like already had a year. And Earth is moving along. Venus is here. I lost Mars. So if I pull this up, Mars is moving there. I can't, oh, I could just barely do it. All right, let me go back to April. And so there's April. You can see Mars down there, May, June, July, and then August. And so you can see the motion of these worlds. So this is really a great tool that I use a lot. You can also go to objects, the planets, and it's got information about all the planets. And you can click on each planet and get more information. So this is, if you want to see what's up in the sky, it's terrific. Here is the path of Mercury. Nope, that's the data. I didn't want that. And so you can click to expand. That's what I wanted. And so here's the map of the sky. And here's Mercury doing its loops. Generally, they're moving eastward to the left. Here it loops. And then here it loops. Here it loops. So this is the motion of Mercury. So this is just a terrific site. And I wanted to show you that where I'm stealing these diagrams. So here we go. So that's all that. And here's this. like little exploding stars there. All right. So this is where we got with the sky. So now let's look at the stars that are out. The brightest star in the sky, north or south, is Sirius. It's not really that's all that bright. It's only about maybe twice the size of the sun, but it's only 9 light years away. It is in the neighborhood. So that's why it is so bright in our sky. And then Betelgeuse and Rigel are stars in the constellation of Orion. Sirius is the dog star. And it's the dog star because it's in Canis Major, the big dog. And in August, when that's when the dog days are. It's the dog star because it's in the constellation of the big dog. But the dog days of August are named that, and it was thought that they're so hot because the light of Sirius is adding to the light of the sun, because the sun is about here in August. And so that's the lore about the dog days. And then here is Aldebaran and Procyon and Capella. Here's Pollux and Castor, the twins of Gemini. So what if it were dark at sunset? What would we see? So let's look at that. Ta-da! Magic. Shut the sun off. And so here you can see the constellations that these stars are part of. And so does anybody recognize a constellation in here? Somebody want to pipe up?
Is it Orion?
Orion, yes. All right, so there's Orion, the mighty hunter. And so he's got his shield here. Rigel is his foot or his knee. Betelgeuse is his armpit. And it roughly translates that name. It's kind of in tortured Arabic. So it roughly translates as armpit of the great one as he's holding his club. So here's his club. And so here, the dog star. So the Orion's belt points at Sirius. The dog star is a dachshund. The great dog, by the way, is a dachshund, but the little dog is a stick. So the big dog is doing okay. So Canis Major and Canis Minor. And then here is Aries. So here's Jupiter, Mercury, Uranus, Venus, and Mars. Here's Aries, the ram. Here's Taurus, the bull, with the pretty little Pleiades in here. And here's Gemini. And so these are the constellations of the zodiac. When the sun is between Earth and these constellations, if that one is when you're born, that means your sun sign is that constellation. And so if you're a Gemini, you've been looking up the Gemini horoscopes in the paper, that means that the sun was in this vicinity when you were born. So we see, remember, Gemini and Orion, these are winter constellations. We can't see these constellations when the sun is in them. So you're born as a Gemini, you can't see Gemini until later in the season because the sun is between you and the stars. And then here is another line. So this is due west, and this line comes up and hits this star, the rightmost star in the belt of Orion, whose name is Mintaka. And this is the celestial equator, the projection of Earth's equator. The stars, so all the planets are moving eastward, left along the ecliptic through the year. The stars each day move 1 degree westward, parallel to the celestial equator. So there's 2 motions going on at all times between the planets and the stars. The stars are moving, of course, because of the rotation of Earth. The planets are moving because Earth and all the planets are in their orbits in the solar system. And then here, notice that here the celestial equator and the ecliptic are close. They're getting close again here. This is the maximum distance between the celestial equator and the ecliptic. And so this is the sun's northernmost position. So that is our summer solstice. And that's why its heat adds to the heat of Sirius to create the dog days. And then over here, we have the cosmic W, Cassiopeia. Take it away. You can see it there. And then we have the hero of the sky, Perseus, here in next to Cassiopeia. He's coming to rescue her daughter Andromeda. And then there's Auriga, the charioteer here with the bright star Capella. And so these guys actually lie along another line, which is the galactic equator. So the plane of our galaxy is along here. And actually, so we live in this frisbee of stars, and we're not in the middle. We're out 3/5 of the way out from the center toward the edge. And when we're looking in this direction, we're looking out of the frisbee. So we're looking out the short part of the frisbee. I should have I don't have a disc. And so we're looking out along the plane, but we're not looking through very much of the galaxy. So this isn't really, it's the Milky Way, but it's not very dense Milky Way. We see that actually in the summer. We'll look at that too. So, and then here is Andromeda. So she's chained to a rock, waiting for Cetus the sea monster to come eat her, because Cassiopeia bragged that she was prettier than any of the sea nymphs. The sea nymphs got fairly annoyed. They went and told Neptune. Neptune he was going to destroy the kingdom of Cassiopeia's husband, the king, Cepheus. And he said, "Oh, no, you can't do that. How can I appease you?" And so Neptune said, "Well, chain your daughter to a rock and I'll have the sea monster eat her." This innocent woman, just because her mom bragged. I mean, it just, the myths are not nice to women. And so all of this is going on. And then here's the Andromeda galaxy. So we're going to lose it for a while. It's going to be lost behind the sun, and we'll be able to pick it up again next fall. So these are the winter constellations. They're being lost in the light of dusk as the days get longer. So, well, let's look at the constellations we're going to see. And so here, this is still at sunset, but now we're looking east. And so there is a bright star, Arcturus, which is rising in the east early at sunset. You can see we see a smattering in here. And so let's name those. There's Pollux and Castor, the twins of Gemini. And then this one is Procyon. This is in Canis Minor, the little dog. And so again, and then here's the zenith. So again, emphasizing this is a lot of the sky. And what if it were dark at sunset? So let's do that again. Let's dissolve the atmosphere. And there it is. And here are Gemini and Canis Minor. All right, we saw those before when we were looking over in this direction. So let's look at this. Can anybody see a familiar northern configuration of stars? Kind of on the left side. I hope some of you were picking out that there it is, the Big Dipper. All right, so that we can always see in the sky. It just goes around in the northern sky, and we can see it all the time. Well, not with the clouds, but when it's not cloudy, you can see the Big Dipper, except when the sun's out. And so from there, these are the pointer stars, and they point at this star, which is Polaris. And Polaris is at the end of the handle of the Little Dipper. And these two stars at the end of the bowl, these are called the guard stars because they guard the pole, and they're Kochab and Furcad. And I love star names. They're very fun to say. And so here is, let's put the bear figure on here. And I make my bear a little different than a lot of them you see, because I want him to have a little more of a head. And so the bear is all of this. Now, the way I find the bear when I'm outside is here's the Dipper. And notice these three pair of stars. They're actually called the three leaps of the gazelle. And this is his tail. And so this is his back leg. Oh, the other way. So I can pick out his back leg and his front leg. And then in here, you just kind of make stuff up. You know, the point of these constellation lines I show you, they are mnemonic devices. That is, they're just to help you remember. So whatever works for you is fine. Nobody has chiseled these into stone. Well, they might be chiseled into stone somewhere, but you can make up your own. It's quite all right. And so looking here between the Big Dipper and the Little Dipper, there's this long twisty constellation called Draco the Dragon. L10 is this the brightest star in the head of Draco. And the star here, right between Kochab and Furcad, and this star where the handle bends, this is Thuban. And for reasons that are challenging to explain, Earth, as well as spinning on its axis, the axis wobbles over a period of about 26,000 years. And so the North Star isn't always the North Star. It changes stars. And when the Egyptians were building the pyramids, the star in here, right there, that is named Thuban, and that was the pole star. That was the star they looked at to find the North Pole. So there are those, and then hiding under the tail of the great bear are the hunting dogs, Canis venatici. And then from the Big Dipper, you can make an arc to Arcturus. So our friendly little bright star there. And Arcturus is in a constellation named Boötes. So the umlaut over the O means you say them both, like cooperate, Boötes. And Neckar is one of the stars in there. It's Boötes the herdsman. It looks like an ice cream cone to me. Right now it's laying on its side, but in the fall it really looks like an ice cream cone. It's even got a little drip here. The little drip's name is Muffred. I always thought that might be kind of a nice dog name, but then everybody just call it Muffy. So I haven't done that. And so then this is faint. You don't see these stars are, why would you pick these out? This is Coma Berenices, the hair of Bernice. So she had longer hair than I did, and she actually cut it off and sacrificed it on the altar of Zeus so that her husband Ptolemy would come back from the war alive. And he did. But this, you can see there's a little cluster of stuff. There's a star cluster there, and there are scads of galaxies. I'll show you one of the images from the James Webb is taken in the constellation of Coma Berenices. So that's why it's worth pointing out. When later in the summer, when you see the handle of the Big Dipper high in the sky, get out your binoculars and just go below it, find Canis venatici, the hunting dogs, just those two stars, and then go a little farther down towards Arcturus. And it's a very glittery part of the sky with bunches of stars. It's really pretty to look at. And so here is a Cancer. And again, this is for stars. But it turns out there's a cluster of stars in here too, very close to this place. And here is Leo. I love Leo. We don't get to see Leo for very long. Comes up in the spring and then disappears quickly because the days are getting longer. But Leo actually looks like a lion. Actually, Leo is thought to have been the model for the Sphinx with his paws out. I forgot, I usually draw this line here out to this star to be his paws out front of him. And so nice star names here, Regulus and Denebula and Zosma and Cherton and Rus Elacid Australis, all right, which is the southern, I can't remember what it is. I looked it up today and I forgot, but we have great names. And notice Elacid, these are, a lot of them are from Arabic. That's because Ptolemy, one of the Ptolemies, they were a busy family. One of the Ptolemies made an atlas of the sky and very detailed, a lot of information, and it spread all over the world, which then was, Europe and the Middle East, Southern Europe and the Middle East. And then the Europeans managed to lose or burn all their copies for, they lost them for like, a couple of thousand years. It turned out that they have found some old copies in monastery libraries in Europe. But in the meantime, the Arabs, they got those atlases, went to Persia, they were translated into Arabic. And so we got back Ptolemy's atlas translated into Arabic. So that's why we have names like Aldebaran, which is the follower, and Betelgeuse, and some that I'll show you in when I look at the summer sky. You got to wait for that. But notice again, here's Gemini, Cancer, Leo. The next one's going to be Virgo, but it's not quite up yet. And so again, the constellations of the zodiac show us where the ecliptic is. So if you know where the constellations of the zodiac are, you can keep track of the planets. So, you know, you got to make these little maps of the sky, just like you make maps of your village, or when you go to a new place, you know, you find the hotel, find from the hotel to the restaurant, the hotel to the museum, and you make your little pathway. You can do these in the sky and gradually learn the whole sky. So, and then here, starting in east, so the projection of Earth's equator goes through due east and due west. And so there is that. And these stars are rising 1 degree per day. And so you can watch these coming into better view. So that's a kind of a neat thing to watch. If you have something in your yard, a pole or something, and if you can line up a star with it one night at a time, and then go the next night and see, you know, it should be a degree to the west. And then over in this part, the southern part of the sky, there is this pretty little star called Alphard. All right, it's another good dog name, Alphard. Alphard, come on back. Okay. Let's look at the sky in high summer. So this is July 15th. So it's light practically forever. So this is 11:30 p.m. at the Roll-Off Roof Observatory. That's what RO is. And so the stars, of course, don't vary in color as much as this program has them varying in color, but well, it does okay. So the brightest star here, well, there's a bright one here, and there's a bright one here. This one is Antares. Notice it's red. And the name of Mars in, let's see, Mars is, I can't remember if it's from Roman or Greek. And then the other mythology has it as Aries. All right. So Antares is the rival of Mars, the rival of Aries, because it's so red, like the planet Mars. And it is in the Scorpion, Scorpio, the Scorpion, Scorpius, the Scorpion. And so here is the Scorpion. And these two little stars down here are called in English the Stinger. But I did my graduate work in New Mexico, where they call those los ojos de la Virgen, the eyes of the Virgin. And parents tell their children, she is watching you. She's always there. And so there's that. And then there's this teapot thing. I was watching the video where people are doing the sky photography, and you have that video. The teapot is moving. You can see it cruising across the sky. Yeah. So here's the teapot and the teaspoon. These are actually Sagittarius. Now, Sagittarius is the archer. And so the teapot, just the teapot's easier to see. But this is actually the bow. This is his elbow crooked. And this is his arrow. And he's shooting at the heart of the Scorpions, because the Scorpions running around the sky trying to catch up to Orion and bite him. So the archer is trying to protect the great hunter. And so this star is Nunki and Acela, and then Caus Australis, which is the southern part of the archer's bow. So that's why we have Australis is always the southern. And so there's those. And then over here is Capricornus. Now this one, so now you can see there's a V, a shallow V and a deeper V. And so, the other way. And so this is a mergoat. All right. You've heard of a mermaid. Excuse me. Pardon me. So you've heard of a mermaid. This is a mergoat. All right. Head of a goat, tail of a fish. And I see it actually as a communicator from Star Trek. I mean, it's not perfect, but it's closer to that than a mergoat to me. But maybe I'm just not imaginative enough. One of the things you think, how did they get a mergoat out of that? But remember, the ancients, particularly before they had writing, the sky was their storybook. And it reminded them to tell stories in their seasons by, oh yeah, that star, oh, the story of that constellation is. And so this is why they really had their culture, and they pasted it on the sky, not that they saw shapes and then named them. Leo, maybe, but the others, not so much. So here is Libra. Here are the best names in the sky: Zubin el-Janubi and Zubin esh-Shamali. They mean the northern claw and the southern claw, because Scorpius actually had the claws out there. We've kind of declawed this poor scorpion now, so I don't know how he's going to actually bite Orion. But notice now, again, we have Libra, Scorpius, Sagittarius, Capricornus. That's the zodiac. So there's the ecliptic. All right, if we're looking for planets, we can look along there, and no, there's no planets in that part of the sky. Saturn has been hanging out in Capricornus for a couple of years, but it's finally moved on. All right, it's moved on into Pisces. So some others. This bright star, remember I said, oh yeah, there's a bright one, and its neighbor is fairly bright too. This is Altair and Tarazed in Aquila. I had it fly in because this is the eagle. All right. I don't think it's an eagle. I think it's a stingray. And that's what it's, it's more of a stingray. And, you can even imagine this is its mouth, and it's got its little stinger there that, wasn't nice to the Australian. But that is Aquila the eagle. And then here, this guy, he looks like he has one arm, but he's supposed to have two. His name is Ophiuchus. And the bright stars, Russell Hogway, and this one, Russell Gethy, is actually a Hercules. But Ophiuchus is the snake bearer. And so here is the head of the snake, Serpens caput, I don't know how you want to say it, Serpens cauda. So this is the head of the snake. This is the tail of the snake. And Ophiuchus is hanging him. The caduceus, the medical symbol with the snake, it's thought that Ophiuchus was a healer holding the snake. And this caduceus, the symbol of medicine, has the snake wrapped around the pole. And so some think that's related to myths about Ophiuchus, and some think, no, it's from the Bible. It's when all the Israelites were getting bitten by snakes, and they had to put a snake on a pole, and if they looked at the snake on the pole, they didn't die of the snake bite. So, but remember, this is the ancient storybook of our ancestors. So it's really nice to know about these guys. And so that's Ophiuchus, and then here are cute little ones. Delphinus and Aquilus. Aquilus is the smallest constellation in the sky. There are 88 official constellations. They fill the sky. They're the political map of the sky. They're like countries and counties and states. They fill all the land on Earth. The constellations fill all of the sky, and it's governed by the International Astronomical Union. And so let me get rid of these. Delphinus is really easy to pick out, really pretty, and it really looks like a leaping dolphin. It's right up there with Leo. Aquilus, I don't know how you get a horse out of that, but well, And then, so this is the celestial equator. So here is south. All right. So the celestial equator stretches from due east to due west across the sky, and it's up at about 45 degrees. We're at about 45 degrees north latitude. So if Earth had rings, we would see the ring plane there along the ecliptic. That would be kind of cool, but it would block a lot of stars from us. So I don't think we want rings, but it would have been cool. So there is the celestial equator. And here is the galactic equator. So remember, when we were in evening sky right after sunset, I showed you where the galaxy equator was kind of arching across the sky, and it didn't really look much like the galaxy. Here, now if I take the galactic equator away, you can see all this, glittery and smeary stuff. This is the Milky Way. And this is a beautiful area to look at. Just grab your binoculars, the chaise lounge, a beverage of preference, lots of bug dope, and, and just lie back in your chaise lounge and just look at this whole glittery area of the sky. And so that's the galactic equator. This is the galactic meridian, all right, which goes through the center of the galaxy. And so what these show us is, well, one, here is the winter solstice. That kind of should have come up earlier. That's the winter solstice. When the sun is there, all right, it's winter, it's December. And so if you're a Sagittarius or a Scorpius, you can't see those constellations in the month you're born because they're behind the sun, because that's where the winter solstice is. And then the other thing we find from the galaxy is that spot. That is the center of our galaxy, 27 light years away, where there is a 4 million solar mass black hole. And they have imaged it. If you go to the, Earth Horizons Telescope? Is that the name of it, Seth? Or, yeah. And where they made a telescope basically of the Earth with different antennas, and they looked at that and created an image of the black hole. So that's a really amazing place. And, we're seeing it as it was 27,000 years ago. But this is the sky we get to look forward to. This is, to me, I mean, people love Orion, but man, I love the Milky Way. I love this part of the sky. Besides, it's warm. Oh, all right, take a break. So, images from the James Webb Space Telescope. So this is their webpage, web.nasa.gov, esaweb.org, and so these are public instruments. This instrument is paid for by the tax dollars of the United States, Europe, and other countries that are contributing. And so all of these images, the data become public very quickly. All the big observatories now are international collaborations. They're so expensive to build and maintain, and also they're getting automated, so they take their images automatically, and then the job of the astronomers is not to go out and look through the telescope anymore. It's to get online, download data, and learn something from that. So astronomy is really changing. We don't have to hang out in the observatory dome freezing to death anymore. So, oh, sorry, I went too fast. So, Uranus. This is an image from James Webb Telescope of Uranus. Wow. All right. Uranus, all right, the Earth is tilted 23.5 degrees away from, the axis isn't perpendicular to the orbit. It tilts 23.5 degrees away from perpendicular. Well, Uranus does like 98. Its pole is like laying right along the ecliptic. And so the seasons last half a year. And the year on Uranus is 84. All right. And so 48 years of summer and 48 years of winter. That'd be pretty tough on Uranus. It's now northern spring. Okay, so we're coming into where the northern pole is pointing at the sun. North, by the way, is defined as, when you look down on north, the body rotates counterclockwise. And so there's a polar cap. This polar cap develops in the north. It develops in the summer, which is weird. And the nice thing about these James Webb images is maybe we'll be able to figure out more of what's going on Uranus. And then there are these bright clouds. Here's a bright cloud. Here's a bright cloud. And notice all the glary stuff here. All right. This is a 12-minute exposure. And so they were, just did this very quickly, and I'm sure they can do better. This is just probably, reflections they can take out with better data processing. So the James Webb detects things in infrared. So in infrared, you see stuff glowing at lower temperatures than the stuff that glows in visible light, right? For an incandescent light bulb, you have to have that titanium filament at hundreds and hundreds of degrees to shine visible light. All right. Whereas dust, warm dust glows in infrared. You glow in infrared. Your cat glows in infrared. All right. The landscape trees glow in infrared. And so we're a lot cooler than that tungsten filament was in the incandescent lights. So that's our image of Uranus. And we could even, this is that image, all right? They blew it up to make the one I showed first. It turns out the rings and the orbits of the moons are also all perpendicular to the ecliptic. And it's like, how in the world did that happen? Did this big swirling cloud of something make itself into rings and moons in that orbit? It's really confusing to figure out how this whole system formed perpendicular, because the rotation of something, it has an angular momentum. It's hard to stop, and it's really hard to flip. So if you try to flip something, you try to flip a spinning bicycle wheel, it doesn't flip, it turns. So how this system came to be is very confusing. So the rings, there are 13 known rings. The James Webb can see 11, and the bright ones, you won't count 11 there because they blur together. And then the moons, there are 27 of them known. Most are just too tiny to pick out in this image. All right, so these are Titania, Ariel, Puck, Miranda, and Umbriel, and Oberon here. And they included this, that north is up, solar system north, and solar system east is to the left. So this whole system is moving to the left along its orbit. And so here, I just grabbed this moons of, here's the URL for this, moons of Uranus, so you can see what these guys, so here's Miranda there, Ariel here, Umbriel is here, Titania down here, and Oberon down here. So these are the largest moons of Uranus, and they're all utterly itty bitty, smaller than our moon. So galaxies, all right, Hercules is loaded with galaxies like Coma Berenices. So this image was taken during instrument calibration. So they weren't trying to do science with this. They were just calibrating instruments, taking pictures. And look at this thing. Look at all these galaxies. I mean, every one of these smudges. All right. Here is a star, and you see this 12-sided spike. That's due to the structure of the James Webb Telescope, the hexagonal mirrors. And so that's a star, and that's a star. Every other smudge is a galaxy. These weeny little red things, these are galaxies. That could be a spiral galaxy like the Milky Way. 300 billion stars. How many civilizations could have lived or be living in that smudge? And to that galaxy, the Milky Way looks about like that. And here we are, thinking we're the only game in town. So this is just amazing. So this is LEDA, and these are initials for a European system of naming galaxies. And so this thing is we see it, it's about 1 billion light years away. We see it as it was 1 billion years ago. So, 1 billion years ago, Earth didn't have plants. All it had was basically pond scum, cyanobacteria. And so if this galaxy is looking at us, all they see on Earth is cyanobacteria. And all these bright bubbles of red, that's where stars are being formed. We can use James Webb to look at those. We can use the spectra to say what elements are there, in what ratios, how are these stars forming, all of this fascinating stuff. And it looks like Leda 2046648 had a baby. This is probably slightly farther away. I mean, we've got to do some extra work to find out how far away that is. It's just, I mean, these pictures, I want one the size of my wall that I can just dive into because they're so amazing, all these galaxies. So, the cosmic seahorse. All right, before I show you that, I want to remind you that gravity bends light. This is what Albert Einstein told us. This is from an article at Forbes. And this is why Einstein knew that gravity must bend light. So you can grab that article from Forbes. And so what happens here is that light from these galaxies gets bent around an intervening cluster of galaxies, and all these different images end up at Earth. So we can see this galaxy, we'll see it up here, and we'll see this same galaxy down here. So we can actually get multiple images of galaxies, of the same galaxy. It's kind of, if you next time you break a wine glass, break the stem off and move the stem around on a picture of a galaxy. And that's not entirely unlike what gravitational lensing does. It warps the images because it's curved and all of that stuff. And so here is the cosmic seahorse. This guy, they've named it the cosmic seahorse. This is a very distant galaxy. We can't see another image of the galaxy because it's too far away and too faint. So the images we have are these ones that have been lensed and they're warped. This lensing cluster, this is in Coma Berenices. All right, this block of galaxies. This is in that dinky little constellation that has, 3 stars that you can pick out only if you work at it. And this is what's lying beyond that. It's just incredible. Here's another Milky Way wannabe. And so, again, astronomers are able to study star formation regions in here. That's where stars are forming. That's where stars are forming. And even this warp. Also, the other thing this does is that galaxy clusters and galaxies themselves, it turns out when we look at how fast the galaxies are moving around the cluster, and we add up all the mass, okay, this is a giant galaxy, maybe 1 trillion solar mass galaxy. This is another 1 trillion solar mass galaxy. This is maybe 500 million. So we can add up all the masses in here and say how much mass this cluster has. It's not a great estimate, but it's a decent estimate. And none of them have enough mass to hold the galaxies. The galaxies are moving too fast. They should be flying off, like going too fast around a curve. And so there's something there. It must be matter because it's producing gravity, but we can't see it. So we cleverly named it dark matter. And so what these warped images also do is that they give us a way to probe the density of dark matter by the way it's warping the image. And with computer modeling, people are starting to do that and learn. This is how we can learn about dark matter, because dark matter, the only way we detect it is with its gravity. Fortunately, that gravity bends light. All right. Dark matter doesn't glow, but it bends light. So that's how we're able to reach out there and try and figure out what's going on. So the nearby cluster is 6.3 billion light years away. The lensed galaxies are much farther. And so they are seen much longer ago. And so astronomers are studying star formation in them. Oh, sorry, I just looked at my watch. I'm sorry, I get so excited. And so here's some more background. This is the same galaxy lensed 3 times. Here's the oldest image. This is 320 days later because the light followed different paths. And this one took 320 days longer to get to us than this one. And this one took 1,000 days longer to get to us than this one. This here, you don't really see a supernova. Here, this star has exploded. And then here it's fading. This is a type 1a supernova. This is where a white dwarf gets too much matter piled up on it and it explodes violently. They all have the same physics, so they all come to about the same peak brightness. We can measure how bright this is. That's what telescopes do. And we can calculate how far away they are. Because of how bright it looks, how bright we know a supernova is, we can calculate the distance. And then this white glow around this cluster of galaxies is diffuse gas and dust held by the gravity of the galaxy. So this is the intra-cluster medium. So, and then here's some more. Let me turn up. So these boxes show green peas. On the early images, they look tiny and green, so people call them green peas. We're seeing these galaxies as they were 13.1 billion years ago. Earth did not exist. And so, yeah, these things, again, very distant galaxies. And we can, BYA is billion years ago, and we can study these things. It's just mind-blowing what we can learn from these images. And so it's just, astronomy is always amazing. So with that, the adventure continues. So sorry I went over time. Thank you all for being here.
There's no overtime in the universe, I guess.
Yeah.
Well, thank you. Thank you.
So,
That makes my brain hurt.
it's cool stuff. It's very cool stuff. It's just so exciting. I mean, you can, when I start surfing any of these things, I just get sucked right down the rabbit hole.
Yeah.
And 3 hours goes by.
Yeah,
Ah.
for sure. Amazing.
Say thank you.
Thank you.
Thank you. I was happy to have you here. Have
Thanks
a good
for-
night.
Night.
Good night.
Any before we head out, any thoughts or questions or anything left unspoken? That
I
13
have a question.
Yeah, Mark Staves, a board member, founding member of the
Yeah.
Adirondack Sky Center.
Thanks for the positive messages in the chat, by the way. I'm seeing them, so thank you.
Yeah.
Yeah, Mark.
So Eileen, knowing that you're a radio astronomer and your discussion covered gravitational lensing, is there any data that you can extract from gravitational lensing on a radio astronomer type?
Oh, yeah.
So there is an
Gravitational
impact.
lensing was first detected by a radio telescope at Jodrell Bank in the UK, in England.
Okay.
Yes, we first detected it, so we see the same thing.
Okay. I was
Yep.
curious about that. Thank you.
Yep, and we can see them in X-rays too. It bends all the light equally. Well, no, it bends it at different angles because of but so yeah, all of the wave bands show lensing.
So 13.1 billion years ago, that's not that far after the
Right. Yeah.
know,
It's about,
Big
700 million years after the beginning of time.
yeah. That's painful to think about.
Yeah. So just Google James Webb images and you can, go down the rabbit hole yourself. It's amazing what they're putting out. The thing I don't like is they put the images on Flickr and I'm not very good at using it. So, but. So any other questions, comments?
I have a question.
Yeah.
It's an infrared telescope, so are all those images false color? And if so, like how do they choose what colors?
Yes, they are. Actually, all modern telescope images are, quote, false color because they're detected electronically. Now, we can take it through a filter and we know, okay, this is a green filter and we can assign it green. But even the Hubble Space Telescope saw into the infrared and we don't see infrared. So there's no color for infrared. The color of infrared is dark. And so, yeah, they do assign colors and often they'll make, they just shift our color scheme down, but they don't use, they use some greens and yellows. So they just shift our color scheme to redder wavelengths. But each image, it depends on the information they're trying to extract. And so on the images, often it will say how they assigned colors. They did that, I know, with the Hubble Space Telescope. You could find out how they assigned the colors. And one of the problems is that in physics, if something is hot, you know, there's red hot and white hot, right? And red hot, is red hot hotter than white hot, or the other way? Which is hotter, red hot or white hot?
White hot.
White hot. Yes, blue in physics is hotter than red, but culturally we see blue as cool and red as hot. So on the Hubble Space Telescope images, they were always kind of torn about how do we do this. So there's a lot of Hubble Space Telescope. They had a whole bunch of artists hired to help them decide the colors in the images. One, to make it easy to discern the information with our human eyes, but also to just make them look spectacular so that the public saw that this is what our tax money is doing, is providing us these spectacular images. So yeah, they're all false colors, but they try to assign them with some logic.
The Hubble used a fairly common formula. It was RGB translated into hydrogen, sulfur, and oxygen, HSO. That was the fairly common translation from RGB to HSO.
Yeah, so they may have something like that with Webb. I haven't looked into it deeply enough because I do radio galaxies. I do radio astronomy, so we just have squiggles.
Mm.
We look at spectra, bright, dim.
Well, if there's nothing else, there's a lot to think about for sure.
Yep.
But with that, I want to thank everybody for
Well,
coming.
thank you, Mary. Appreciate that.
And thank you, Eileen. This is always enjoyable, entertaining.
Well, I always have a great time.
Yeah, no, it's contagious. How could you
I
not?
just get carried off. So, yep. All right.
So-
Well, thank you all for coming out. Geez, you guys are, tenacious too. You stuck it out till the end,
Yeah.
so.
All right. Well, thanks
right.
everybody.
And you'll
we'll
be able
see
to
you-
find this on our YouTube channel too.
That's right. Sometime over the weekend, you'll be able to find this in addition to all of our other lectures in the Cygnus series from the very beginning. So sometime over the weekend, take a look for that. We'll post it on our Facebook page as well. So thanks everybody. Clear skies, and we'll see you on May 4th.
All right. See you
Good
all.
night.
Bye. Thanks.
Well, that was fun.
That was great.
It
Yeah.
was fun. Thanks, Mary.
Thank you. It was awesome. Just awe-inspiring. Wonderful.
Well, thanks. It's the stuff. That's
It
gonna be
really
fun.
is the stuff. It's the stardust we're made of, isn't it?
Yeah.
That's
yeah.
right. Yeah.
Very-
Eileen.
We're gonna have to answer that question about why Uranus is tipped that way.
I
I
know,
get asked that
it's-
question more than anything else about the planets.
Yeah. Yeah. It's weird.
Yeah.
Yeah. The angular momentum is just, how did that happen?
Yeah. Was it just far enough away that I don't know. I'm not
Yeah.
gonna make it up, but that's very strange. So, all right.
All
Well,
right.
thanks. We're gonna decode this into a video file, and we'll get it up on our YouTube channel as quickly as possible.
All right. Sounds good. I think
So-
I'm going to leave my office.
I think you
Thank-
did well deserved. Well deserved. Have a glass of wine.
Night.
All right.
Good night.
Good night. Hey, Mark. See you later.